Now let's talk about the acid-base properties of alcohols and amine. But before we continue, we will talk first about the acid and bases. So if you think you are competent in acids and bases and you still remember all the basics, then maybe you can skip this video. If you want a reminder, then please watch this video because we're going to discuss what are acids and bases. So there are three different definitions of acids and bases. The Arrhenius definition, Brunister-Lowry definition, and the Lewis definition. So the Arrhenius definition is that an acid is a substance that dissociates in water to give the hydronium ion H3O plus, where the oxygen has three hydrogen, so it has a positive charge, and a base is a substance that dissociates in water to give an OH negative or a hydroxyl group. The Brunister-Lowry definition of acids and bases is that an acid is a species that can donate proton, and a base is a species that can accept a proton. The Lewis definition of an acid and base is an acid is an electron pair acceptor. So we are not talking about protons here, but we are talking about electron pair. And a base is an electron pair donor. So let's have a look at these ones. So generally speaking about acid and bases, so the dissociation in water. So if you have an acid like hydrogen chloride, HCl, and in water, what will happen is that the HCl will dissociate in water. The water will take the proton or the hydrogen from the hydrogen chloride, and the hydronium ion will be formed. And then the hydrogen chloride will give us the chloride ion. Now, remember that HCl is the acid, and when the acid dissociate, it will give us what's called a conjugate base. So the chloride ion in the media here is called a conjugate base. So an acid will give you a conjugate base. In this dissociation reaction, water here acts as a base. So water can act as an acid or as a base. So the water as a base, where it acts as Brunister-Lowry base, so it accepted a proton, then it will give an conjugate acid. So hydronium ion here, this is hydronium ion. This is conjugate acid. For bases like amines, for example, amines are bases here. So nitrogen with a lone pair of electron, it will, or amide here, which means that we have a nitrogen which has a negative charge. Now the nitrogen will accept a proton from water in the media, so it will dissociate to give ammonia as a conjugate acid. So the base here will give a conjugate acid. Water here will act as an acid and will give hydroxide ion, which we call conjugate base. So basically, conjugate base is the base that's formed from the acid, and the conjugate acid is the acid that is formed from the conjugate acid is the acid that's formed from the base. So the strength of both the Brunister-Lowry and the Arrhenius acids is expressed by the extent of the ionization of the acid or in water. So the general reaction of any acid, HA, it's an acid, it's a source of hydrogen here. We are talking about the Brunister-Lowry and Arrhenius because they both need to have a proton. The acid need to have a proton. So the dissociation in water will give you the hydronium ion and will give you the conjugate base of the acid, which is the A with a negative charge. Ka is called the dissociation constant, and the acid dissociation constant equals the concentration of the product divided by the concentration of the acid itself. So the concentration of the conjugate base and the conjugate acid and the conjugate base formed divided by the concentration of the acid itself. The magnitude of the Ka will represent the relative strength of the acid. So the stronger the acid means that it has a more tendency to dissociate in water to give the conjugate base of the acid and the hydronium ion. Then the Ka will be of larger value. So the higher the dissociation, the stronger the acid, the higher the value of the Ka. So strong acids in general are almost completely ionized in water, and the Ka of strong acids will always be greater than 1. For weak acids, which are most organic compounds, so organic compounds are not strong acids but mostly will be weak acids, they will have a Ka less than 10 to the power minus 4. So because of the value of the Ka will be very small and the exponent will be very high with a negative charge, then we express that with a smaller value, so we express it as pKa. So pKa is basically the minus log 10 of the Ka. So for example, for water, so water in water will give you a hydroxide ion and hydronium ion. This is the situation of water in water. The Ka of water is the concentration of the hydronium times the concentration of the hydroxide ion formed divided by the concentration of the water itself. And the value of the Ka is 1.8 times 10 to the power minus 16. So the pKa of water is 15.7. So 15.7 is quite a high number for pKa, and that means that water is a very weak acid, because here, as you see, the Ka is 1.8 times 10 to the power minus 16, so it's a very low value of Ka. So normally, because pKa is minus log 10 of Ka, the smaller the value of the Ka, the weaker the acid, the higher the value of the pKa. So we would know that strong acids generally have a pKa values of 0 or less than 0, so it's a negative number. Weak acids generally will have a pKa value more than 4. The weaker the acid, the larger the pKa and the smaller the Ka. Let's have a look at the table to the right here. So hydrochloric acid is a strong acid. It has a pKa of 3 minus 3.9. Hydronium itself, not the water, but hydronium is still a strong acid, and it has a pKa of minus 1.7. Looking at the organic acids here down the table, you see that acetic acid is a weak acid because the pKa is 4.7, and it's stronger acid than barium ion, which is 5.2. And this is stronger than phenol, which is 10. Water is a weaker acid than the phenol, and alcohols here, like ethanol, are weaker acids than water, and so on. Ammonium and then ethane. So as we go down, these acids are weaker. How can we predict the direction of the acid-base equilibrium? So when you react an acid with a base, so it will be a certain direction, whether to the formation of the conjugate acid or base or to stay in the original form. So in order to predict the direction of acid-base equilibrium, it's important to remember the following. First thing is that acid-base reaction always favor the formation of the weaker acid and the weaker base. So that means that we need, if the acid is stronger, then its conjugate base must be weaker. Okay, so it will favor the formation of the weaker base. And if the base is strong, then it will form a weaker conjugate acid. So the stronger the acid, the weaker its conjugate base, and the weaker the acid, the stronger its conjugate base. So that's why strong acid will tend to dissociate, and because it will form a weak conjugate base. And the weaker acid will less favor to be dissociated. It will stay in its undissociated form, and because the conjugate base is stronger. So let's have an example. So now if we have something like HCl with water, its dissociation, it will favor it to be the dissociation to form the chloride ion and the hydronium ion. HCl is a strong acid, and the chloride is a weak base, a weak a conjugate base. something like methanol in water to give methoxide and hydronium. So the methanol itself is a weak acid, and the methoxide itself is a strong base. So now for methanol, it will favor to be in the undissociated form because it's the weak acid here form. For the HCl, it will favor to be dissociated because the base is the weaker form. So remember also that this arrow here, the two arrows, means that this reaction or this dissociation is reversible, yeah, meaning it can go both way, this way and that way. And if we draw one arrow in a bigger form, or if it's bigger like this one, that means it will favor to go to the right. And if it's smaller, that means it's less favored to go to the left. So now for here, for this one at the bottom, because the arrow that is going to the left is a bigger arrow, that means that the weak acid is more favored to be formed, and the methanol will stay in its undissociated form. So it's a weak acid. Generally speaking, the more stable the conjugate base, the more acidic the acid from which it comes. So there are three factors that affect the stability of the conjugate base. So we need to look at why the conjugate base will be more stable. The more stable the conjugate base, the more it's favored to be formed, and the weaker the conjugate base. So there are three factors that affect the stability of the conjugate base. These are the electronegativity, size, and resonance. So what is electronegativity? We said that the electronegativity is the tendency of an atom to accept electrons, and its tendency um, to attract electrons. So the more electronegative the element, the more easily it can bear a negative charge. That means if it can easily bear the negative charge, that means it's more stable as a conjugate base. So because the stability comes here from the ability of the atom to accommodate the extra charge. So if we have something like carbon, the carbon does not actually cannot bear a negative charge. And a carbon with a negative charge will be very weak or highly unstable. But something like oxygen can easily bear negative charge, and that means it will have some acidic property. Its conjugate base will be stable. So let's have a look across the periodic table. So across the period, we have the carbon is less electronegative than nitrogen, which is less electronegative than oxygen, and which is less electronegative than fluoride. So the electronegativity increases across the periodic table, across the period as we go to the right. That means for the conjugate base formed, the one that forms from the carbon, which is the carbon with a negative charge here, it will be much less stable than the nitrogen with a negative charge, which is less stable than the conjugate base that's formed, which has a negative charge, and it's less even than the fluoride with a negative charge. If we consider the acidity now, so because these are more stable, as we go to the right, it's the conjugate base is more stable. That means the acid they come from are stronger. So the methane is not acidic at all, and then ammonia or NH3, it's a weaker acid, much weaker. It's actually more like a base. And then water it's a weaker acid. And then finally, the hydrogen fluoride is a stronger acid compared to them. Because the fluoride ion itself, it has more stability as a conjugate base, so the acid that comes from is a stronger as a base. On the other hand, the basicity will increase as the stability of the conjugate base decreases. So now the fluoride is less basic than the OH, which is less basic than NH2, which is less basic than the CH3. So the more stable, the less the basicity. The more stable of the base of the conjugate base, the less its basicity. The other factor is the size. So the negative charge of an anion is basically an element or an atom or a group of atoms that has a negative charge. This is called an anion. So the negative charge of an anion is more stable if it's spread over a large region of space. So within the column of the periodic table, the size increases as we go down. So we have fluoride, chloride, bromide, and iodide. They are all halides on the same group of the periodic table. The size increases in this direction as we go from fluoride to iodide. That means the iodide itself is stronger. The conjugate base of the iodide with a negative charge is it's more stable than the bromide, which is more stable than chloride, which is more stable than the fluoride. That means that the acidity of the acid that they come from is more stable in the same direction. So hydrogen iodide will be stronger as an acid than hydrogen bromide, which is stronger than the hydrogen chloride, which is stronger than hydrogen fluoride, because the size of the anion that's formed as a conjugate base can actually accommodate the electrons better than the smaller size. The third factor that affect acidity as well, or the stabilization of the conjugate base, is the what we call the resonance. And this is more important in organic compounds because we cannot see resonance in organic compounds or in organic acids. So for the resonance is basically the movement of electrons without any atom leaving. So, for example, if we have something like the acetate anion that's formed from the dissociation of acetic acid, you will have a negative charge on the oxygen because the acetic acid you have CH3 and then C with a double bond O and then OH. So when it dissociates, the hydrogen here will leave this proton, leaving a negative charge here on the oxygen. So this negative charge or this extra lone pair of electron here on the oxygen can undergo something called resonance stabilization. The resonance will come here from the fact that this electron can move here to form a double bond with the carbon, and then this double bond here will move to give a negative charge on the oxygen. So now you have one negative charge that is distributed between two different atoms. So the conjugate base formed is actually more stable because now not only one atom will have the negative charge all the time, but it will be distributed between two different atoms all the time. So this is the arrow which we draw between the different resonating structures we have. So the difference between the first and the second one, the first one you have the negative charge on this oxygen. So you'll have a negative charge on this oxygen, but the second one you'll have the negative charge on the other oxygen. This is due to resonance. As you see, no atoms left at all. It's just movement of electron, including the double bond. So it's only double bond that or triple bond that can move the electrons, but not a single bond. So it's sigma bond do not take part in resonance. It's only free electrons or lone pair of electrons and the double bond. So if you compare that with something like ether oxide ion, so ether oxide ion is the ion that's formed, the conjugate base that's formed with the dissociation of ethanol, then you will have a negative charge on the oxygen, and then there will be no resonance at all because there is no double bond here. So if this bond moves to, if this electron moves, these two electrons move to make a double bond here with the carbon between carbon and oxygen, this is not possible because now it means the carbon will have 5 bonds and carbon cannot have 5 bonds. And there is no double bond where we can break. In order to make the carbon has 4 bonds, then you have to break one of the sigma bonds, which is impossible in this case. So there is no resonance stabilization in this case, and the ethanol is a very weak acid because the conjugate base is unstable. This will make it unstable. So the pKa of ethanol is 16, while the pKa of the acetic acid is 4.7. That means it's a stronger acid than ethanol. Something like methane sulfonate, which comes from methane sulfonic acid. Now it has a methyl group attached to a sulfur that has three different attached with three different oxygens. So the methane sulfonic acid, there is a hydrogen here with this oxygen, and then it dissociates to give a negative charge on this oxygen. Now notice what will happen. So first, for resonance stabilization, the extra lone pair of electron can move to make a double bond here with the sulfur. At the same time, this bond can break this way. So now you will have a negative charge on the oxygen at the top. There's another one that can also form. So now this extra lone pair of electron on the negative charge can move to this bond to make a double bond. And then this bond can break, the double bond here can break to give a negative charge on the oxygen on the bottom. Again, these arrows here, the double-headed arrows here refer to the resonance. Okay, so it's different from the dissociation. So remember the different shape of the arrows when we are talking about the reactions. So now we have the negative charge distributed between three different oxygens, not only two like the acetic acid. This is why methane sulfonic acid is much stronger as an acid because the conjugate base is much more stable, and the pKa now is minus 1.2. It's a strong acid, not a weak acid like acetic acid. So this is how the resonance affect the stability of the conjugate base and make the acid stronger. The final thing you need to remember about acidity and basicity is that a non-proton Lewis acid, because we also said that there is a definition that is Lewis, this definition, Lewis acid and Lewis bases. So the Lewis acids are known as electrophiles, and the Lewis bases are called nucleophiles. So electrophiles from the name phile means lover. So electrophile is a species that loves electrons. Okay, so they have the ability to accept electrons, so they act as electron acceptor. This is why they called electrophile. Nucleophile is a species that that likes the nucleus or love the nucleus, meaning it loves the positive charge, so it must have a lot of electrons it can donate, so it acts as electron donor. This is why for the Lewis definition, we said that acids are electron lone pair of electrons acceptors and the Lewis bases are electron donors. In organic chemistry, we will usually deal with the name electrophile and nucleophile, especially when we are talking about reaction mechanisms. So it's very important that you get yourself familiarized with